For part E, automatic so is connected or drives a constant load. So of what? Of 2 kilo ohms. So that's 20 sine omega t, and that one is 20 ohm. So this is the load RL. This is Rn. Draw the circuit and calculate the error and the voltage delivered to the load because of the source and the resistance. Assuming that there is no source, internal resistance, so this is 0. To find the ideal, you need to assume that this is 0. And there's no internal resistance. So the circuit is like this, basically. It's 20 sine omega t, and this is 2k ohm. So what is V in that case is equal to what? The voltage in that case. V load is going to be equal to Vn, which is the same one, so it's 20 sine omega t volts. Okay, so that's the ideal. Now, given this error, so given this internal resistance, the new voltage will be like a voltage divider, voltage VL. So we're gonna get the ratio between this resistance and this resistance. So this resistance is relative to the summation of both, so it's gonna be multiplied by the end voltage. So VL is equal to RL over RL plus RN multiplied by Vn, which is this. This is Vn. Okay, therefore it is 2000 over 2000 plus 20 multiplied by 20, which is or 20 sine theta, sine omega t, which is 19.8 sine omega t volts. Okay, now, so this is the real or the actual. Now, what is the percentage error? As we said before, it's actual minus ideal or theoretical ideal over ideal times 100%. Therefore, it is 19.8 minus 20 19.8 sine omega t 20 sine omega t over 20 sine omega t. If you notice, you can just simply cancel out sine omega t because it's common. Sorry, let me just go down all the way. So out, out. So you'll end up with basically 19.8 minus 20 times obviously 100%. This is gonna be 0.99% or minus 0.99%. As you can see, the sine omega t, including whatever omega t is, omega is the angular frequency. So whatever this is, it does not affect the fact that the error will always be 0.99. That takes us to the second part of the question, which is when error. So the source or the error is independent of the frequency of the source, because it gets cancelled out anyways. So for question F, capacitive pressure sensors exhibit the capacitance. So for pressure sensors, usually capacitance is directly proportional to force. Okay, so basically, yeah. So in this, the relation is given as E is equal to 1 plus 10 microfarad. This means that we have a sensor. The sensor is exactly like a capacitor. It's a capacitor that changes with force. So F is equal to the force applied, and the unit of which is microfarad. Okay. So the question, the sensor works over the range of F is equal to minus 1n to F is equal to 1 plus n. So F can take a value from minus 1n to 1n. Minus 1n meaning pulling, 1n meaning actually pushing. Design a bridge to turn the change in pressure into the change in voltage. The bridge should be balanced with no forces applied to the sensor. Derive an expression for the output voltage for your bridge circuit and determine the extremes of voltage output possible. Use the full range data sensitivity, assuming MV over N, and MV over N, assuming linear response. So this is the shape of the bridge, the bridge circuit. So, and this is the output. Okay. So when we say design, the question is asking you to give values, but then he's giving you one condition. When F is equal to 0, meaning that there is no force applied, the bridge is balanced. Here it says when F is equal to 0, are balanced when no forces applied, meaning F is equal to 0. So if F is equal to 0, what's C gonna be? The sensor C is gonna be basically F is 0, so it's gonna be 100 plus 10 multiplied by 0 is 100 farad, microfarad. Okay, so that's the value that we have. Now, by balance we mean at this 100, so this is 100 microfarad at 0, right? So we need this, the output, to be 0, and this means that C1 over C should equal to, at F is equal to 0, C1 over C, this is a given equation, this over this should equal this over that. So R1 over R2. Now, we know C, right? But we don't know C1, R1, or R2. And we don't need to know them, we're actually choosing them. So for easiness, I will choose this to have the same value as this, so 100. So let C equal to 100 microfarad. Therefore, C1 over C is equal to 100 over 100, which is equal to 1, which is supposed to be equal to R1 over R2, meaning that R1 over R2 is equal to 1, therefore R1 should equal to R2. So whatever value we choose to R1, we choose to R2. So for easiness, let's just set R1 and R2 equal to 1 kilo ohm. So here 1 kilo ohm, and here it's 1 kilo ohm. Here it's 1 microfarad, and here it's 100 microfarad, actually 100 plus 10 farad, 10 force microfarad. Okay. So when F is 0, this is balanced. When F is not 0, there is a voltage here. So when F is 0, V out is 0. Okay. So now, what's the next step? The next step is to actually calculate the output voltage at any given time. You see, V out is basically, at this part, it's the voltage across this, VC, let's call it VC, and as the voltage across VR. So V out is equal to V out is equal to VC minus VR2. Okay, what's VC? VC using the potential divider, so basically we're dividing this, over the summation of both. The same goes for here, this over the summation of both. So it's gonna be 100 plus 10 farad over 100 plus 100 plus 10 microfarad plus 10 F. Okay, so 100 plus 10 F over 100 plus 100 plus 100 plus 10 F minus what? Minus what? Actually multiplied by Vn. So multiplied by Vn. This is all Vc. And now minus VR2, which is VR2 in that case is what? 1 over 1 plus 1. 1k over 1k plus 1k divided by Vn. So Vn as a common factor. So Vn outside, which is 10. Put it outside, and then you have 100 plus 10F over 200 plus 10F minus 0.5. Therefore, this is the output. So whenever you push on the sensor, V out changes, giving this equation. So now we solve the first part of the question, which is express output voltage. We break and determine the extremes of the output. This is the first part. Second part is determine the extremes of the output. So by extreme we mean it takes value from -1. This is the minimum. Maximum is 1. So substitute 1 time F is equal to 1 and 1 time F is equal to -1. So same equation here, but we substitute F by 1 and -1, and this is the answer. The maximum voltage you get is 238.1 megavolt, and the minimum is -263.2 megavolt. Okay. So for the last part, sensitivity. Sensitivity has a unit of millivolt over N, which is force. The way you calculate it is basically, it's simple. Maximum voltage minus minimum voltage over maximum force minus minimum force. So 238.1 minus, between brackets, minus 263.2 over 1 minus 1. Minus 1. So this is the answer, 250.7 millivolts per Newton.